Today on the Perception in Action podcast, the second part of my look at perceptual motor development, this time from the ecological perspective. If it's not pre-programmed by our genetics, how does a child's pattern of movements emerge from the dynamical constraints of the environment? And how does movement shape perceptual discovery? So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. Back in episode 38, I discussed how traditional theories of how infants learn to control their bodies assumed that this process was highly similar for everyone because it was mostly determined by physiological maturation. If you look in most psychology textbooks, this is clear. If there is a discussion of perceptual motor development, it will typically be seen in a section that discusses things like growth charts, simple reflexes, and milestones. We also saw that early researchers in this area were very wrapped up in the nature versus nurture debate. That is, the extent to which our development is determined by our genetics or our environment and experience. It is for these reasons that perceptual motor development became a pretty stagnant field of inquiry after the late 60s. There is not much more description of the milestones that could be done. Arguing about opposite ends of a strict dichotomy rarely gets resolved and ends up being pretty dull. And with it being a universal, biologically grounded process, there weren't really many interesting questions for a psychologist to ask related to perception action in this area. Enter the ecological psychologists of the early 90s to give the field a good kick up the backside. The seeds for this revolution in thinking about perceptual motor development were actually sown in 1967 in the fantastic work of Nikolai Bernstein, who I discussed back in episode 15 when talking about the idea of freezing and freeing degrees of freedom in movement control. If you remember from the discussion of the traditional approach last time, in the models of researchers like Gessel and Brunner, learning to produce a complex action like a child reaching to pick up a toy was a relatively straightforward process. Simple actions, like fixating the toy with the eyes and opening the hand, what Brunner called subroutines, were pieced together like a set of Legos and fine-tuned based on internal feedback from the efference copy. Where did the simple subroutines come from in the first place? Well, returning to my Legos analogy, they were like a mysterious gift from Santa. As Brunner described in his 1973 paper, these were evolutionary, quote-unquote, pre-adapted behaviors, passed down through our genetics via neural codes we were born with. So again, not much for psychologists to directly study. The other main consequence of this approach is that there is really only one way to perform each action successfully, by getting the subroutines in the correct order, basically. Bernstein rejected this idea of these pre-adapted routines, and instead argued that movement coordination occurs by a process of cooperative interaction, in which the system has access to the full menu of possibilities. So, instead of being told that you have to pick up an object by holding your hand upright and closing it just this way, you are free to pick up an object using any of the myriad of possible abilities of your hand, arm, shoulder, and body. Use just 2 fingers, scoop it with the palm of your hand, bend at the waist, put your back into it, etc. This idea had several important consequences for researchers interested in perceptual motor development. First, it introduced a tricky new problem to solve. How exactly do we choose between the almost infinite number of menu options when making a movement? What Bernstein called the degrees of freedom problem I discussed back in episode 15. Second, it opened up the possibility of large individual differences in development processes, since there is more than one way to produce the same movement. Third, it effectively created a separation between motor development and physiological growth of the brain. An easy way to understand this is to think about what happens when you contract your pec muscle in your chest. If your arm is hanging down at your side, sending the command to your pec muscle will cause your arm to move forward in front of your body. But if you're holding your arm straight out to the side, this exact same command will cause your arm to move upwards towards your head. I've included a picture of this in the show notes. This means that there can't be a simple pre-adapted neural code for movements. If that were the case, we would only be successful in our actions in certain contexts. for example when our arm happened to be in the right place to start with. Or, alternatively, we would have to have stored in our brain 1 million possible neural codes for every possible combination of starting positions of every muscle in our body. As Kugler and Turvey put it, movements cannot be perfectly pre-planned. Instead, they must be what they called softly assembled, ready to be adapted for the particular context in which they're being performed. The final contribution that Bernstein made in this area really was to provide a roadmap for finding the solutions to the problems he identified. Although there were these infinite menu options in possible context, the degrees of freedom in movement were actually limited by the constraints imposed by our body, what ways we can move, and the environment, the opportunities for action. When Bernstein's ideas began to be fully recognized years after they were published, it was a game changer. As Esther Thelen, who you'll be hearing more about shortly, put it, quote, "In light of Bernstein's insights, the simple picture of the infant waiting for the brain to mature and then, like a marionette, executing the brain's commands was clearly untenable," unquote. And the psychologists and movement scientists rejoiced. There was a new complex problem with multiple interacting parts to solve: perceptual motor development. So, if every movement a child makes is a unique, flexible solution that depends on the specific context in which it occurs, the timetable of motor development cannot be encoded in our genetics and have a perfect one-to-one relationship with our physical growth. The alternative view inspired by Bernstein also provided a very simple solution for a problem that was very difficult to handle for traditional theorists: regressive or U-shaped behaviors in development. These are behaviors that appear, then seem to disappear for a long time, only to reappear again much later. A good example of this is stepping behavior. When a newborn infant is held over a floor, they will exhibit coordinated step-like movements. These movements quickly disappear in a couple of months, only to reappear again near the end of their first year, just before they're starting to try to walk. Why would a neural code for movement give something, then take it away? The answer is it doesn't. As Thelen and Fisher nicely showed, this behavior can be understood easily by looking at the mutual constraints imposed by the child's leg strength and their mass. In the first few months of life, we have a rapid gain in weight that is mostly fat, thus increasing our leg weight without a similar increase in leg strength. So, the movement that was possible with a newborn's constraints is outside their ability until their leg strength catches up again. In dynamical systems terms, leg strength is a rate limiter in this example. This can easily be shown by immersing a young infant torso deep in water, which of course will decrease their effective leg weight. The lost stepping behavior will suddenly reappear. This is a good example of how the development of movement behaviors does not follow a perfectly pre-planned sequence of milestones, but rather arises online as a product of multiple interacting factors, not just our genetics. Researchers like Esther Thelen have modeled the stepping example and many other behaviors using the idea of an attractor landscape. That is, based on the constraints and dynamics of the infant's environment, there are certain patterns of behavior their perceptual motor system will be quote-unquote attracted to, and they will always tend to return to these even after being perturbed. This leads to short-term stability. However, in an infant, this landscape is always changing, giving rise to instability and eventually phase shifts to a completely different set of behaviors. This idea of an attractor landscape puts paramount importance on the role of exploration by the child in the developmental process. New behaviors like walking and crawling are not just genetic instructions waiting to be unlocked. They must be learned as the child chooses a menu of motor options to assemble adaptive patterns of movement based on their own dynamics and those of the environment. In the ecological approach, it is assumed that this exploration is motivated by a task. For example, the child's desire to get a toy in their mouth or cross a room to get to a family member. This places a much stronger influence on the role of the environment than what we saw in traditional theories. In the traditional approach, it was really the presence or complete absence of environmental stimulation that mattered, While in the ecological approach, not only must the environment be present, it must be rich enough to provide the infant with complex tasks that must be solved. Another nice example of this can be seen when you look at a child's behavior in a jolly jumper. For those that have never seen one, this is a device with a set of springs and a harness which suspends the child and allows them to move to bounce themselves up and down. Anyone who has seen a child in one of these knows they can be amused for a long time by producing what looks like very boring, repetitive bouncing to us. In a study published in 1993, Goldfield, Kay, and Warren developed a model of this. The model predicts that the bouncing behavior of the infant should depend on the device's resonant frequency. This is the natural frequency it vibrates at. Think of a person playing music by touching the rims of a set of glassware. They are triggering the resonant frequency of each glass. With the jolly jumper, if the child moves so that the device bounces at this frequency, they are essentially going to get more bounce for the ounce. Lots of fun up and down motion with minimal amount of effort. And this is exactly what was observed in the study. Over time, the resonant frequency acts as an attractor, and the child adjusts their kicking patterns to match it.
I'm gonna give it all to you, 'cause that's the only thing to do, 'cause baby I'm in love with you.
Another key question in the ecological approach is how does a child develop the ability to use perceptual information to control their actions? In particular, how do they learn affordances and come to know whether they can successfully perform an action or not? As I discussed briefly back in episode 38, this work really started in earnest with the excellent research of Eleanor Gibson. Using a device she created, Eleanor was able to demonstrate that almost as soon as they began crawling, infants can use information related to the depth of objects in their environment to detect whether or not a surface affords falling. Since that initial work, more subtle variations of the visual cliff have been employed, using different types of surfaces. For example, when faced with having to walk across a waterbed, toddlers will typically explore the unsteady surface for a moment, then switch to crawling. Another excellent developmental researcher, Karen Adolph, has looked at how infants deal with having to crawl down a steep ramp. As slope steepness increased, toddlers about 14 months old became increasingly wary, hesitating and touching the slopes, often refusing to go, sometimes scooting backwards, but rarely falling. Younger infants of about 8 months of age who are still crawling do not seem to pick up the affordance as they plunge down the hill and often have to be rescued from falling by the experimenter. So clearly, sometime between the age of 8 and 14 months of age, a child learns to pick up the perceptual information provided by the sloped surface and use it to guide their actions. From this initial work, Karen Adolph has gone on to do a highly systematic and thorough examination of perception of affordances in walking and crawling. I've included a link to a review paper in the show notes if you're interested in hearing more. As I discussed back in my interview with Duarte Araujo back in episode 18D, a less well-studied but equally important issue in this area is the opposite side to this coin. So not just looking at how perception guides action, but looking at how action shapes perception. This is a particularly important issue when we look at development. Each time a child develops a new perceptual-motor competency, they create new opportunities for exploring their environment and discovery. For example, transitioning from crawling to walking allows the world to be viewed from different angles. The importance of actions in shaping how we perceive the world was demonstrated nicely in a study by Bushnell and Boudreau in 1993. In this research, the authors examined the abilities of infants to perceive properties of objects through active touch, what is called haptics. For example, when can a child discriminate surface temperature or object weight or roughness? Interestingly, it was found that this completely depended on the type of hand movements they were able to perform. When they were really young and they could only clench an object in their hand, surface texture and hardness, which require the ability to slide one's hand across an object or poke it, could not be perceived. This perceptual ability did not come until the motor ability was there at the age of 6 months. Perception of weight does not come until even later, when the child can make more subtle finger, arm, and hand movements. These are great examples of how our ability to act, or move constrains how we perceive the world, and that when we develop new action capabilities, we open up a range of new perceptual opportunities. This can, of course, also be extended to cognition. For example, the work of Piaget I discussed in my last episode. How we can act on the world shapes what we can know about it. Before I wrap up today's episode, I wanted to mention some more recent research that is particularly relevant to many of the amazing abilities of elite athletes I typically discuss on the podcast. Here I'm referring to the development of the ability to use motion information, which I discussed in detail way back in episode 5 and many times since. This issue has been investigated in an excellent series of studies by Ruud and Audrey van der Wiel from the Norwegian Institute of Technology. In their research, the van der Wiels used a combination of brain recordings, specifically EEG, and behavioral responses such as eye blinks and reaching movements. The EEG work is in many ways similar to the baseball research I talked about with Jordan Maraskin back in episode 25D, in that they are looking to see if the child's brain produces EEG responses that differ as the visual stimulus is changed. One of the interesting questions they've looked at is how a child follows with their eyes and reaches to grab an object that gets occluded from view. At about 8 weeks of age, infants begin to show the ability to smoothly pursue moving objects with their eyes and continue to improve in this ability rapidly up to about 14 weeks. At about 6 months of age, they reach for a moving object by not aiming at the current position of the object, but predictively aiming for a position further ahead on the path where the hand and the object will meet. Looking at hand and eye movements, sometime around 48 weeks, infants anticipate the trajectory of an object passing behind an occluder. They start moving their hand before it disappears so that their hand will be in the right place to intercept the object after it comes out the other side. If anyone is familiar with the developmental research of Piaget, this ability relates strongly to the development of Piaget's stage of object permanence. The van der Wiel's reaching work actually suggests this occurs much earlier than Piaget thought. Another question Ruud and Audrey have addressed is when do infants become attuned to the best information sources? For example, when looking at defensive blinking responses to virtual looming objects, they found that the youngest infants they studied used a strategy based on visual angle, or the distance to the object, to time their defensive blinks. Thus, they blinked too late when the object approached at a higher speed. As the infants got older, on the other hand, they began to use a more effective tau or time-based strategy, allowing them to blink early enough for all the approaching conditions of virtual motion. This research also provides evidence for the effect I discussed a few moments ago, that perceptual abilities are directly linked to the actions the child is able to perform. In particular, this was shown by looking at an infant's response to optic flow that is normally produced as we move through the world. Infants were presented with 3 motion conditions: forward optic flow, reversed or backwards optic flow, and random visual motion. EEG recordings showed that 11 to 12-month-old infants can differentiate between these 3 motion conditions, with the shortest latency occurring for forwards optic flow and the longest latency occurring for random visual motion. Younger infants could not do this. Only the older infants who had crawling experience and of course experienced self-motion themselves were able to distinguish between the motion conditions, while younger infants who only had passive locomotion experience from being carried around could not. The final important issue the van der Wiels have examined is how being born preterm affects sensitivity to motion. Preterm children have been shown to have deficits in the perception of global and biological motion, which I discussed with Kylie Steele back in episode 37C. In reaching studies, it was found that preterm infants continue to reach too late for moving objects and use the ineffective distance strategy for approaching ones. Without interventions, such deficits can persist even when the child reaches the age of 14 years. So, to sum up, in today's episode, we looked at the ecological approach to perceptual-motor development. In this approach, the idea that the movements a child performs are prescribed by their genes and follow a set pattern of distinct stages is completely rejected. Instead, movement patterns are thought to emerge based on the task the child is presented with and the constraints imposed by their body and the environment. Instead of being perfectly pre-programmed, behaviors must be soft-assembled and adaptable. This leaves open the possibility of using different solutions to reach the same goal. We also saw that perception-action relationship flows both ways. Perception guides action, but action also opens up a world of new perceptual information for the child. Well, that's it for today's episode. Coming soon on the Perception and Action podcast, can a holistic goals approach make athletes perform better under anxiety? As always, you can email me at robgray@asu.edu, follow me on Twitter at ShakyWeights, and find out a lot more about this podcast at perceptionaction.com. This is Rob Gray from ASU. Cheers for now.